What Louise Prockter, is the director of the Lunar and Planetary Institute, is going to talk about is getting more into the geology of Europa, based upon what we learned from Galileo. And Christoph referenced this, and I think it's important to touch upon over and over again. Galileo told us a lot, but in reality it didn't. We only have 10-ish flybys, close flybys of Europa. And I think in the past 10 years we've been sort of, we've lost sight of that with Cassini's experience, where we flew by Titan, 100 and some odd times. We flew by Enceladus 12, 14 yeah. So it's important to always come back and realize that as exciting as Europa is, our data set on it is woefully inadequate, or woefully below what other more modern missions have shown us about their targets. Nevertheless, Louise and other scientists like her have been squeezing that data set beyond getting water and blood out of it. I don't know what you're squeezing out of it at this point. But the cascade, the waterfall, the torrent of data and discoveries we'll get from Clipper will remedy a lot of this. But Louise will give us an idea of the current state of the art that we currently have.
Okay, I don't know about state of the art. Let's just say we're very jealous of Mars. Constantly. We've been jealous of Mars for 20 years. Okay, so as Kurt did this wonderful introduction, so I am going to talk today primarily about the observations of the surface of Europa and what we've learned, or what we think we know, what we infer about the shell from those observations. So I'm going to stay mostly away from the modeling and the constraints on the shell from those. We're going to be talking about those at length over the next 3 days. So first of all, obviously we're all pretty much in agreement that Europa has an interior ocean, although it was not always the case. There was a paper in 1998 or 99 led by Bob Pappalardo, where we went into great detail about whether or not Europa even had an ocean, and we evaluated all the evidence from the surface morphology primarily about whether the surface features could be explained by liquid water ocean, or whether they could be explained simply by ductile ice below the surface. But I think now pretty much everybody is in agreement that there is a liquid water ocean there. I don't think anyone disagrees with that. But there's still a lot of disagreement about how thick the ice shell is. Although generally in the community I think we all are on the side of a thicker shell. But the purpose of this workshop is accessing the oceans of icy worlds, and especially we're interested in Europa since we've got at least one mission upcoming. And I wanted to talk especially about how thick that shell is and the difficulties that may be inherent on accessing the shell, and what we're really talking about here, and make sure that people really understand the possible challenges that we're going to face. And that we're not deluding ourselves as to the difficulties there. And so I'm going to step through some of the issues that we're going to have. So the temperature structure is pretty straightforward. Obviously, if it's a thin ice shell, it's going to be conductive. If it's a thick ice shell, it's going to be conductive and then convective underneath. And I'll step through why. Kurt mentioned the Galileo coverage. This is just a map showing some of the resolution, which I'm not going to go through in detail, but very high resolution, less than 0.5% is at 10 meters or better. We actually have exactly 2 images of the surface that are at better than 10 meters per pixel, just a couple of strips at 12 meters or better. So you can't even resolve something the size of this room, and so we're talking about putting a lander down on the surface. So it's very difficult to really evaluate what that means. Globally, we have better than 1 kilometers at about 70% of the surface. We're still using Voyager data in some of these regions. We simply don't know really what is there. So a lot of the surface we're looking at sort of postage stamp sized areas, or we always joke about how we just start seeing something interesting and then it's right on the edge of a mosaic and we can't really trace what's going on the surface. So we have a lot of questions about the stratigraphy of the surface, the age of the surface. We think we know the age and the sequence of things, but then we still don't have the global picture, so we are making a lot of assumptions. We do think we know that there are 2 main styles of deformation on the surface. One is ridges and bands, which I'll talk about a bit later. Tectonic deformation, heavily overprinted, multiple episodes of deformation. We don't really see anything like this anywhere else in the solar system. And the other type is what we call chaos terrain. For obvious reasons, it is utterly chaotic. One seems more lateral in extent, and the other seems more vertical in its expression on the surface. Christoph mentioned this a little bit, but tidal deformation. Europa is in an eccentric orbit. We wouldn't be able to notice it, we wouldn't be able to tell that this was happening. It's very, very tiny, it's 0.01%, but this is enough of an orbit to create a bulge as Europa goes around Jupiter. And this bulge is there, it happens every 3.5 days, so this tidal bulge is pulled towards Jupiter and it pulls up a radial tide, and we think that if there is indeed an ocean below the surface, that tide is going to be on the order of about 30 meters in the ice shell. If there was no ocean there, it would only be about a meter on the surface. And that bulge librates, it tries to face Jupiter's center of mass at all times, and that tidal deformation causes a dissipation of energy, and that tidal energy we think is focused in the softer part of the icy shell. And that misalignment promotes something we think is non-synchronous rotation. The shell is actually decoupled from the interior. I'll talk a little bit more about that in a moment. But this 3.5 day cycle as Europa goes around Jupiter causes the shell to undergo stresses, so it's rotating over the tidal bulge, or it's moving over this tidal bulge, and that causes areas of tension and compression on the surface. Let's see if I can get this. So areas in red are tension and areas in blue are compression, and if this works, which I don't think it is working, as the shell moves over the areas, over the bulge, these rotate around. And so any crack that happens to form on the surface is going to meet these areas of tension and compression. And so the orientation of those cracks can change over time as they meet these different areas. And what that means is that cracks on the surface will change orientation depending on where they are when they form in Europa's tidal cycle.
Do the cracks that you see on the surface roughly match this orientation?
Some of them do, yes, and I'll get to those in a moment. Yeah, especially things called cycloids, they match very well indeed. One other kind of stress that we see is the non-synchronous rotation. I mentioned earlier that we think the shell is decoupled from the ocean. Someone asked a question earlier about grounding. The ocean is simply too deep for any grounding to occur, and we don't think there's topography that would be deep enough. Although we would measure that if we were flying by the gravity, I think the signature would be high enough. Non-synchronous rotation is something that we think we have evidence of it from the orientation of lineaments that don't match our tidal stress models. And some early work, first from Voyager and then more recently from Galileo, looking at the orientation of these lineaments, suggests that they don't meet the current stress fields, but if you go back in time, you can go back sort of maybe 30 or 40 degrees and fit them to previous stress orientations, suggesting that the shell has perhaps reoriented. The shell is slipping forward faster than the rest of Europa, or slipping beyond Europa. And so it's going faster than the synchronous rotate, or it has done that in the past. However, more recent analysis led by Lissa, she looked at one area in particular of Europa and couldn't make that work. I think you actually found a better fit by a totally random analysis, so you didn't find that non-synchronous rotation worked. So I think the jury is still out on this. You included other stresses, including obliquity. So the idea of non-synchronous rotation, we still need to look into that some more. It may be that it does happen, but it just happens very slowly. And there are some other stresses as well that need to be taken into account, and I'll talk a bit more about those later. One of the features on the surface that does appear to have a big component of the diurnal stresses are these ridges. Some of these are very large. They can be almost hemispherical in their orientation. They come in various different flavors, starting from just simple cracks through to very complicated multiple solar lineaments. The most common are these sort of double ridges. They're trough with two sort of almost very linear hills next to them. They're extremely uniform in length, many of them are. And there have been many models proposed to try and explain them. Here are some of them, ranging from simple volcanism, crack forms, liquid water comes up and a spray comes out of the sides and forms these nice ridges each side. Tidal squeezing, this is from an Earth analogue from the tidal leads in the Arctic ice, I think, or Antarctic ice, Arctic ice, I guess. Tidal squeezing model. So the ice comes in, you pull the ice apart, you get a slush forming in the crack, and then you push it back together and keep forming that to form the ridges on either side. Diapirism, that upwarps the ridges on either side. Compression, this is a problem, is how do we accommodate extension, and maybe shear heating. There is an element of strike slip along a lot of these ridges, and so shear heating is another one. And then Keck, who's also in the workshop, has a new model suggesting that sills can also form the ridges. But despite 20 years of data and models, I don't know that we're particularly far forward in understanding how ridges form. It's very hard to explain all of the models. However, the form of them, the cycloid form, can be very well explained by this diurnal model. And if I can make this work, this is modeled by Greg Hopper and colleagues, which shows that the rotating diurnal stresses match very well. You can form one of these arcs in each daily cycle, and the idea here being that it's a tidal walking model where you form a crack in an extensional stress regime. The crack opens, it moves a little bit in extension. So I should say that these are right lateral in southern hemisphere. You see strike slip right lateral in southern hemisphere, left lateral in the northern hemisphere. The crack moves and then it clamps back together again as the stress closes, and then opens again, moves, closes. And these match almost perfectly the model. So this is a very nice example of the model matching the observation. Unfortunately, we don't do this so well in most of our other models and observations. But you need an ocean for sufficient tidal amplitude and stress for these to form. We can't model all of the ridges in this way. It works very well for the cycloids. It doesn't work so well for some of the other ridges. And we haven't quite figured out how we form the double ridge morphology, but it works very well for the cycloids with the double stresses. One of the other stresses is used to form these small circle depressions. These are very large troughs. They are extremely deep. They're almost a kilometre deep. They seem to form, they're partial troughs, they seem to form these small circles, and they don't seem to fit any current diurnal or proposed non-synchronous rotational stresses. And you can see here, just for scale, how large they are. And they are pretty young as well. They cross-cut almost every feature that we can find them on. And you can see here, this is another great example of how we don't have wonderful imaging from Galileo. We can't trace them across the whole surface because we have a lot of missing data. But Paul Schenk and colleagues worked on these, and they propose that they are examples of true polar wonder. You can reorient the shell by an episode of 80 degrees of true polar wonder, which would be the case if you had variations in thickness in the shell, which is something that you would get if you had a lot of tidal heating, which I'm not going to go into here, but that's something we can discuss more in the workshop. Another area which is evidence of a mobile lithosphere is these things. They're pull-apart bands. They tend to exploit double ridges, and they result in a lot of extension across the surface. This one region probably has about 40 to 50% extension in it. If you zoom in on them using the wonders of either paper and scissors in the old days or these days Photoshop, this is what they look like now. You can take out the bands and put them back together almost perfectly using pre-existing structures as piercing points. This one's exploited two of these pre-existing ridges here. we noticed early on that there's a great similarity to mid-ocean ridges, and what Rob Sullivan did first noticed this, and we took this further and noticed that the interior morphology is very similar to the morphology you see both on mid-ocean ridges in the mid-Atlantic and the East Pacific rise, and the morphology seems to correlate perhaps with spreading rate. And there's been some new modelling by Sam Howell and Bob Pappalardo. I think Sam is here, right? Hello. So maybe he'll tell us more about this later. But he's suggesting that differences in the band morphology is actually a function of the lithospheric strength at the time of band formation, where in a very weak ice shell it allows convection to basically bust through the lithosphere, whereas with a stronger ice shell you're getting a lot more just fracturing of the shell without this upwelling of the convection cell. This is Ganymede, not Europa, don't confuse you, but the process would be similar on both, and you would get the more ridged morphology of the bands with the stronger ice shell, and the smoother bands would be more prevalent with the weaker ice shell. And you're suggesting that with the weaker shells you could entrain material from very low and bring it right up to the surface, so this could be very good for astrobiology. So hopefully we'll hear more about that. And then some more recent work that I did with Simon Canhorn. We've been trying to find out how all this extension is accommodated for years, and it's been very difficult. Some of it may be accommodated along ridges, but a lot of them don't show any evidence of contraction. But we did find a large missing area in this region, Falger Regio, in the northern hemisphere, and we think we finally found some evidence of subduction on Europa. But we don't think this is subduction in the classic sense that we find it on Earth, where a plate just dives straight down into the interior. We think this is more what we're calling subsumption, where one plate dives into the warmer subsurface of the shell and gets subsumed. And we don't see any topographic signature on the surface for this. And this also suggests that we've got a fairly thick shell going on there. Just wanted to mention something about topography. Castalia macula is a low albedo area. It's here. Just zooming in, it's this dark spot here. This is the Castalia itself, but it's nestled between these two very large dome features. And some photometry analysis by Patricio Figueiredo, and then we did some, Paul Schenk and I did some topography analysis. We actually show that the southern dome is 750 meters above the surrounding terrain, and the northern dome is 900 meters. And the depression here, this dark material is actually sitting in a depression that's about 350 meters below the surrounding terrain. And of course, we were not in orbit around Europa with Galileo, so we don't have a geoid, right, or the uroid, right? We don't have, we only have relative measurements, but we have total topographic amplitude in this area of 1,250 meters, so this is pretty huge. So anything that supports something this large has to be pretty substantive, okay? You don't do this with an ice shell that's only a few kilometers thick. It's got to be pretty major. And this is also a fairly young feature. It has chaos on it and around it. You know, it probably is a chaos region, although surrounding it there's a lot of ridges and bands which tend to be older. So, you know, it must be fairly thick in this area to accommodate that. I want to talk about chaos, these regions of wide-scale disruption on the surface and lenticulae, which are probably the same type of disruption but much smaller. You can see these are sort of subcircular features. From Voyager it wasn't clear what they were. People thought they might be impact craters because they just didn't know. If we zoom in on some of the lenticulae, you can see that they have a lot of fracturing around them. This is a sort of microchaos feature. This is probably transitional between a lenticular and a chaos region. Some of them have flooding, sort of ponded material around them. And the chaos, when you zoom in, this is one of our highest resolution images, about 12 meters per pixel. They are plates. This is Connemara chaos plates surrounded by a sort of disrupted matrix material. So this is that plate here zoomed in. This is Marias chaos, the mitten, one of the largest ones. And this is Theramacula, or is it Thrace macula? This one is interesting because you can trace the pre-existing material going into the chaos. It almost looks like it's it's just melted in situ. It doesn't have the big plates that Connemara has. So even among the chaos regions, we see a lot of different types of morphology, suggesting that the thermal regimes that caused them may have been very different. So something here has just kind of disrupted the brittle shell. These two may have had a much greater thermal component, or the brittle portion of the shell was thicker at the time that they formed. Just an overview of the convection. So we think they form from convection in the ductile portion of the shell. It has to be a certain thickness in order for convection to occur. Okay, so one idea is that the shell has been thickening with time, that maybe it was thinner when the bands formed, and then became a certain thickness which allowed convection to kick in, and then chaos formed. Chaos is younger than bands, right? That's what the stratigraphy tells us. That's what our geological mapping tells us. Ice shells can convect if grain size is small enough, and if you get tidal straining. And there's been work that suggests that warm plumes can rise from the base of the shell pretty rapidly, about 100,000 years. I think that's Metrian Bar. Oh, sorry, Metrian Showman. But it's hard getting through this stiff ice at the surface. Okay, you've got to do something to break through this brittle shell. And so you need some kind of compositional buoyancy to do that. You can get through, you can get up there with thermal buoyancy, but to break through you need some kind of compositional buoyancy. And this is why we don't know enough about the composition right now. We need to know that. So what kind of constraints can we put on our models for chaos formation? This is Connemara chaos. This was kind of the first chaos region that we really saw with the Galileo nominal mission, and we went back and re-imaged it with the GEM mission, the Galileo Europa mission. We knew Europa was interesting, we wanted to go back and see more. So we imaged it 3 times, and some of the highest resolution images came from here. And this is some work that Nicole Spawn did, where she kind of did a jigsaw puzzle on this. She took these plates and she tried to reconstruct them and put some of these lineaments back together, which you can see here. And this is a horrible image because it's from one of the old papers that was scanned back in the days when we had to do that, right, and then post it on the web. But she found that 78% of the plates had undergone horizontal translations of 1 to 5 kilometers, which I seem to have lost from this caption. And 81% of them had rotated by an average of 11 degrees. And what this means is they must have had elevated surface temperatures. And these are big plates, right? These plates are several kilometers in size. And they had moved over a very mobile substrate, right? So this whole area is over 100 kilometers. And so these plates hadn't just disrupted and then frozen in place, as you might expect when you're hitting a vacuum of space. They had moved quite a significant amount. And some of them had tilted, some of the smaller plates had even turned over. And so what had happened to allow these plates to be so mobile after they had broken up and formed? And so there are 2 end-member models for chaos. One is that they're just sitting on liquid water, right? Very popular in the early days. And one is that they are sitting on top of a big diapir. This one is very hard to support just from thermodynamic reasons. It's very hard to create enough energy to melt a big area as large as Connemara chaos. And in the Europa book, which I hope if you don't all have it, you'll all have it by the time we get to Europa with Europa Clipper, because it's a really useful book. Collins and Nimmo did a really nice review chapter on chaos, and they went through, they chose the 6 major models, and they looked at all of the observations of chaos, and they systematically stepped through and went through, could they meet all of the observations. So they went through the melt-through model with liquid, diapirism, warm ice, brine mobilization, so invoking this low melting point brines to help partially melt the surface, partially melt this brittle layer, brine mobilization with liquid underneath, formation of a sill underneath chaos, and then an impact, because there is work out there that suggests that chaos is formed by a large impact, even though we don't see any secondary craters around it. And they stepped through all of these and systematically checked off yes, no, maybe. And they ruled out everything except the brine mobilization models. These were the only two that had yes or maybes under every category. And even here, there were some things that needed more study, but they were able to rule out all of these. These models were expanded by Brittany Schmidt, who's also either here, I think, in her 2011 paper. She showed that the chaos matrix domes and depressions could be explained by a model that was also based on work in the Antarctic, where if you form a melt lens and use brines, hydraulic flow through brine fractures, you can actually have floating blocks that then slowly freeze and dome up on the surface. And you can create lakes under the surface and create the same kind of morphology that we see under particularly Thera macula, and she suggested that might even still be forming on Europa. So this is very exciting. And then recently, Mike Manga and one of his students, I think Chloe Michaud, last year published this paper, which I really liked, suggesting that saucer-shaped sills under pits could explain pit spots and domes, lenticulae morphology. So where you would crack this, the surface underneath a laccolith, and the edges of the laccolith would slowly start turning towards the surface to create this saucer shape. And they show that you can essentially reproduce all of the morphologies, and that liquid water could be present currently under pits 1 to 5 kilometers below the surface. So this is a very interesting paper. I am starting to run out of time. So impact structures, what do impacts tell us about the surface? All impact features on Europa are greater than 4 kilometers in diameter, as shown here. There aren't very many. The surface is between 40 and 90 million years old, very, very young by planetary standards. And multi-ringed impacts, we've only got 2 that we think penetrated through thick ice. We've got these 2, Callanish and Tyre. We can tell from the basin morphology that they have gone through into a ductile layer, right? There's a Malosha-McKinnon model that suggests that if you have a brittle layer that deforms elastically on the timescale of an impact and a ductile layer underneath it, you can the ductile layer will deform and drag the brittle layer into concentric rings. If you go through into a water layer, you would expect to see radial fractures, which we don't see here. So we know this didn't go into water. And you can predict ice thicknesses of about between 12 and 16 kilometers here. This is Callanish, Tyre is similar. So we can constrain the thickness of the ice from these impacts. And then with peak ring basins, this is Puil. This is thought to be the youngest impact on Europa. It's very bright rays, and it also has a peak ring that is 0.5 kilometer high. Again, hard to support that with just a thin shell. But it also has a very low depth to diameter ratio, which means that it's undergone some kind of viscous relaxation. There's probably some ductile ice there, deformable depth. The transient crater diameter for peak ring basins on ice shells is predicted to be very similar to the depth at which they impacted. So we think that the depth under Puil was at least 15 kilometers when it formed. So again, both of these impact features show us that we're looking at a fairly thick shell. I did want to say something about the plumes. What does the plumes tell us about the thickness of Europa's shell? Because on Enceladus, it looks like the Enceladus plumes are bringing up ocean material, right? We're seeing evidence of silicates in the Enceladus plumes. It's possible that Europa's plumes may have a source in the ocean or a lake in the ice, but it's more likely it is a lake in the ice, or maybe even warm, shallow ice. If the ridges on Europa are undergoing strike-slip deformation, it's possible that we're just getting ice coming off frictional ice. It's frictional deformation of those cracks that is releasing ice, and it's subliming into the surface, or we're looking at something that's coming from a shallow lake it is very unlikely that those plumes are coming from the ocean, because the ocean is probably too far away. I'm not going to go into this. I wanted to put this in just for the rest of the workshop, but this is from the Billings and Cattenhorn paper, where they list, this is a little out of date, but they list all of the thickness estimates for the ice shell based from mechanical flexure estimates, mostly the elastic part of the ice, very thin, so this is just the top portion, based on flexure and non-flexure, so these are usually less than a few kilometers. Then they get into impact cratering, so now we're getting down to up to about 20 kilometers. And then thermodynamic analyses, where really we're now getting up to about 30 kilometers. And I added in Quick and Marsh. They had an estimate recently of 28 kilometers on the ice thickness, and then a couple of other ones. I'm nearly out of time, so I can quickly go through this. I think most of you know the mission concept for the Europa Clipper, but it's going to launch. I've probably got about 5 more minutes. Am I going to, like, is this a hanging offense?
This is very important.
Okay, and then I've got like about 3 more slides at the end, just as an overview. Okay, so the Clipper is going to currently launch in 2022, could arrive as early as 25. It is not going to go into orbit around Europa, but it is going to do multiple flybys around Europa. So it will encounter Europa. So it doesn't get the geophysics that we would like. So it will not measure the gravity directly by going into orbit. This makes it a little more tricky to measure gravity, and it doesn't carry a laser altimeter. But it will do multiple encounters, so it will get great imaging. The objectives, pretty straightforward: characterize the ice shell and subsurface water, understand habitability through composition and chemistry, and understand the formation of surface features and sites of recent activity. These are the instruments that it carries that are very blurry. Sorry about that. The most relevant to the ice shell are the camera, thermal imager, the radar, and the gravity. The imager will do high-resolution stereo imaging in color and global imaging, which also supports the radar, because the radar needs to remove clutter from the surface. The radar is very important, right? This is the most important part of it. It does, it's dual mode, sorry, this part here. It's dual mode, so it does 15-meter resolution from about 300 meters below the surface to 3 kilometers, and then it does 150-meter resolution from 1 kilometer to 30 kilometers. So it may get to the ice-ocean interface if the ice is cold and clean, right? We don't know if it is. If the ice is warm, which is more likely, and it's convecting, that's going to be more difficult for the radar to get through. And if the ice is full of impurities, also likely, it's going to be harder for the radar to get through. So we don't know, but we're going to do a very good job of characterizing the top part of the ice, and we're certainly going to understand more about how some of these features form. The thermal imager will help us look for hot spots. It will help constrain where some of those plumes are. And the gravity science will help to understand the time-varying tides, K2, and that will beat down the noise with every flyby. So we think about halfway through the mission we will have K2 to a reasonable level. I'm not going to talk about this. We will do some very low altitude flybys, but we're going to have very nice near global coverage with the imager, so we'll be able to tie together all the stratigraphy. We will, I think, certainly be able to understand how all the features form that we can't do right now. And this is just a hypothetical example from one of the many previous studies we did, but this just shows you how by taking all of these instrument measurements together, we can start to get to a number on the thickness of the ice shell. Very briefly, I wanted to mention the lander. If we do end up sending a lander, right now the lander study contains a seismometer. The seismometer, of course, would get us a very nice ice shell thickness, which would make life a lot easier. Just to wrap up, this just shows you how much we know about Europa's surface age compared to how much we know about the ages of the terrestrial planets, just to put that into context. The mapping we do have suggests that we've transitioned from ridge plains to chaos, and that the activity may be waning, which is very strange even for a surface that is only 40 to 90 million years old. This is just some modelling by Hauke Hussmann that shows there's possibly some cyclical tidal heating and geological activity. And so we don't know how the shell thickness has changed, or if it has. One model suggests that we're looking at both ridged and band formation and chaos formation, so this represents chaos in black, that they may be happening simultaneously, and that they always have, and that our models are wrong, that our mapping is wrong, because we haven't seen the whole surface. This one suggests that we're looking at a very special time, that chaos is just happening now, we just happen to be around to see it. We have no idea what's happened before. This suggests that there is some cyclic thing, that is just an ongoing cycle of bands, chaos, and this just happens all through Europa's history. And D suggests that our impact models are wrong, and that bands happened, then chaos happened, and we've just been fooling ourselves, and that Europa's surface is actually pretty old. And it's a lot older than we thought, and maybe a lot less interesting than we thought. So just to summarize, multiple lines of the geological evidence suggest that Europa's ice shell is very thick. It's over 15 kilometers thick. There is ample evidence for recent liquid, frozen liquid on the surface, but it may not originate directly from Europa's ocean. There's no evidence to suggest it comes directly from the ocean. I bolded this. There are probably thin portions of the ice shell, but they're likely to be situated above subsurface lenses of liquid or warm ice, okay? I don't want to get everybody down right at the beginning of this workshop, but I really need to make this point very clear, because if we're going to drill into the ocean, I'm not sure we're going to do it in our lifetimes. You know, it's going to be a long time coming. But I do think that we can go a long way towards drilling into these subsurface lenses of liquid or warm ice, and whether that liquid comes from the ocean or not, you know, that's something that we can figure out. And data from the Europa Clipper mission and a potential future Europa lander would definitely constrain the structure and thickness of Europa's shell. Thank you.